target, which is exactly in the middle of the concrete, which is not the edge here. As you can see, he keeps on hitting the middle of the target.
Yes, but then here, it's clear it's not flat, right?
Yes, but we can see that
the surface is not flat.
Yeah, but we can see that it hits the middle of the concrete, and the angle of the of when he hits it, we can. Here I neglected it.
Okay, your time is running out.
Yeah. Okay. Okay. So from based on my calculation, there will be no kinetic energy difference, which means that the ball maintains its kinetic energy before and after the impact, which means there are no energies transferred to the wall, which also means that the wall cannot crack, because if it maintains the original velocity and energy, there are no energy transferred to the wall. That is my point.
I don't think this is correct, because the velocity cannot be the same, right?
It shouldn't be the same, but
you need to. Okay. I understand movie is also impossible, but also your calculation is impossible. There's no way the speed is the same. So you need to take a more realistic number. Okay.
Okay.
And then how much you need? How many times you need to hit the ball?
Sorry?
Okay. Why don't you do this? Just use this 0.7. Okay.
Yeah.
Not the same speed. Okay.
Yeah.
Then just calculate how many times you need to hit the ball to make it crack.
Okay.
Okay?
Okay.
Let's do that.
Okay, thank you.
Okay. Thank you, Ken Jong, right?
Hi. Can you hear me?
Who are you?
I'm Pine, 6218.
Okay. Fine. Okay, fine.
Yep.
Found you.
Yep.
Okay.
Yep. Can I start?
Terry, please make it 3 minutes and then make a loud noise. Because
Okay.
we are behind the schedule, right?
Yes.
Okay. Let's go.
Okay. So right now, let's analyze what happens when the ball hits the wall. So, yep.
Okay. Is this the same scene as Kenzo or different?
Same scene as Kenjeon, but like I'm gonna take it further from here. Yeah.
Okay.
So you can see like there's no visible crack on the wall with the normal human force. So yeah. Okay.
Wait.
Sorry?
Is that you hit the? Is that you hitting the wall?
Yeah.
Oh, okay. You made a video. Okay.
Oh no, that was Ken in the video. Yeah. Yep.
Kenzo.
Yep, Kenjeon. Yeah. Okay.
Okay.
Yep. So I'm gonna calculate the impulse to calculate the force. But then firstly, to calculate the impulse, we need like momentum, basically. So this is just a sneak peek of the momentum. So I just use the same as 49 meter per second, but I think I will modify in the report. So yeah. For the velocity here, we use 49, and then if we calculate the momentum, in the movie, we got 22.05 kilograms meter per second. And then let's continue to the impulse. So impulse is a change in the momentum created by the force applied over a contact time. It's given by the formula here. J equals to delta P, which is also equals to force times a change in time, or like contact time. So from the movie, the momentum change of the ball is, if we plug it in the numbers here, it's negative 441 newtons. So in real life, based on the video, the momentum change is much smaller, which is around negative 16.2 kgms. And then if we calculate the force, we can see that it's negative 162 newtons. This comparison shows how the movie exaggerates the force, by nearly like not 2 times, but like 3 times from the real life value. So now let's talk about the Newton's third law. For every action, there's an equal reaction and opposite reaction. In the movie, the wall exerts a reaction of 441 newtons, and which is enough to like visibly damage the wall. But then in real life, it's 162 newtons, and then we can see in the video, it's too small to cause a damage at all. So this contrasts and highlights how the movie implies both action and reaction force for dramatic effect. So finally, now we can calculate the crack in the wall, and this is a pressure, and then we're going to use the pressure to prove that. So the pressure is defined as P equals to F over A. A is the area overall that's touched by the object, and then the force. So basically assume that the ball contacted area is 0.005 meters square, and then the pressure in the movie is 88.2 kilopascal, and in real life it's 32.4 kilopascal. For comparison, the compressive strength of for the concrete is around 20,000 kilopascal. So it needs to exert pressure of like 20,000 kilopascal to even like damage it. So to make a crack basically. So however, in the movie, the illusion of superhuman strength, it's like used and then modified to make this value happen. So in conclusion, while real life physics predicts no visible change to the wall, but like in the movie, it exerts or exaggerate the equations and then manipulate the laws of physics. Yep.
Okay. Yeah, fine. That's good. Okay. In your report, can you calculate what do you need to do to make the crack?
Okay. So
think about a method to make a crack, right?
Yep. Okay.
Either make the ball faster or the ball bigger.
Yep. I'll make the velocity faster, and then also I'll change the velocity in the movie because it will change the calculations, right? But then if it is like extremely fast, but then the thing is like in the movie when it comes back, it doesn't even like decrease in velocity because like when it bounces the wall and it comes back, there should be a decrease in the velocity. So I will also include that too. Yep.
Sounds good.
Yep.
Also, we don't know the soccer ball is the same ball as ours, right?
But then, because we use the FIFA's regulations.
Changing the material of the ball. Okay, please consider changing the material of the ball.
The material of the ball will be explained later by the 2 of the members. Yep.
Oh, okay, that's
yep.
good.
Okay.
Good.
Yep. Thank you.
Thank you.
Okay, so hi, my name is Laura. My student ID is 204.
Okay, Lola, I found you.
Okay, so my name is Laura, as you already know. I'm presenting with Ryosei, and we're going to present you the fireball kick scene. So let's get to it. Okay, so I'm going to use the cursor to point out some values as I'm speaking, okay? So we all know that energy must come from somewhere. So for the ball to create a fireball out of a kick, then we must conclude that the energy must be a lot. But how much exactly? We are assuming, according to these sources, that the main material used to make this football, like our regular footballs, is polyvinyl chloride, or PVC, which has a combustion energy of around 16,900 joules per kilogram. So if we assume the maximum possible velocity that a ball can reach, and the average maximum velocity that a ball can reach, and the mass of the ball, according to this source too, we can calculate the kinetic energy and then compare it to the energy that we would need to reach for the ball to actually ignite, which we can get by multiplying this value by the mass of the ball that we're assuming. And when we compare both of these values, we conclude that the energy that we are reaching, the kinetic energy that we're reaching, is not nearly enough for the ball to ignite, of course. But if we just leave it here, it would feel a bit rushed, so let's keep calculating. But before I tell you anything else...
How did you get the
Yes?
Energy of the PVC to ignite. How do you get this number?
The combustion energy, you mean? This number? Do you mean this number?
Yes.
According to this source, Jefferson's lab, it's a lab funded by the U.S. Energy Department.
Okay.
Okay.
Okay, fine.
Okay. So the stagnant temperature, which is an equation that I'm going to use later, but I'm going to explain now, I'm going to tell you some facts that we are running off of, right? So, so we know that once the ball is in the air, and it goes like at a really fast velocity, the air molecules will be disturbed, which creates aerodynamic forces. This is a very condensed version because we don't have a lot of time. So, so we know that the air molecules will be disturbed because it will produce aerodynamic forces. We also know that the speed of this equation, which is the Mach number, is based on the ratio of the velocity of the actual ball divided by the speed of sound. Also, we are going to base off our calculations basically out of 3 temperatures, which is static temperature, the temperature of still air, dynamic temperature, which is related to the kinetic energy of ordered motion, and then total temperature, which is the sum of these 2. So if air slows down and is compressed by the ball, we can calculate the stagnation temperature to well, of course, know the amount of heat that we're looking at. And we can calculate the stagnation temperature because at stagnant point, the stagnation temperature and total temperature are the same. So let's get to it. We are going to set stagnation temperature to the temperature that the ball would need to be at to actually ignite. And since we're looking for the speed here, because the question that we're looking for is how fast would the ball need to go to actually ignite, we are just going to isolate m, and we get that the Mach number is around 255, which if we multiply it by the speed of sound, we get that it is around 877.2 meters per second, which is over 2 times the speed of sound. This will create a sonic boom, and it's not possible by a human. It's not something that we can produce out of a kick. But now my partner Ryose is going to give you a more realistic perspective. And that's my presentation. Do you have any questions?
How about the friction if the ball is rotating?
Oh, in this case, because of the stagnant temperature equation that we're using, we did not account for friction, but I can definitely include that in the report. Even then, if we accounted for friction, I think that it would still be at least sonic speed.
I agree. Yeah.
Yes.
Okay, very good, Laura.
Okay, thank you so much.
Hello, can you hear me? Can you hear me?
Yes.
Okay.
For you.
I'm Ryosei Nagaki. Student number is 263.
Oh, I remember you. Okay, go Ryosei.
Okay, so right now, we got the ball speed of 877.2 meters per second. So to ensure that this speed is actually impossible to generate it, we need to consider the human capabilities. So by using the number of v equal to 877 and duration of time of 0.01 and a mass of ball for 0.45 kilogram, we can get a force of 39,465 Newton to produce this amount of velocity. So by comparing this force and the average maximum force from that can be generated by a kick, which is 3,000 to 4,000 Newton, we can say that it's more than 9 times the average max kicking force. So it's easy, like it can ensure that it is impossible to generate this force by human leg. So by considering these calculation and equations and considering the energy, acceleration, and force required for a soccer ball to reach ignition temperature, we can say that it's beyond human capabilities, and the ball would need to travel at speed much higher than like the maximum speed that human kick into. So this is if the movie scene actually follows the physics law, the clip should be like this. So it doesn't go straight with fireball, it just falls down before it reaches to the goal. So
You're too weak. You're too weak.
sorry, like, yeah. I am, yeah. Okay, so can I move forward? Okay, so during our preparation for the final presentation, we found out that there is one more group who did the same movie, and one of their clips are exact same as our scene. So to make it to make our presentation more detailed, these are differences between our groups and one of past groups. So main target is same. Kicking a soccer ball and igniting it is impossible. But for ball material, we consider the polyvinyl chloride, which is PVC, while the other team use rubber for that. We use PVC since the most of soccer ball currently used are made of PVC, and from the movie we can see that there's not big difference from the current soccer ball we're using now and their ball. And for ignition mechanism, we assume that the ball got ignited with air compression, so that we can use the stagnation temperature equation, while the other team didn't mention about it, and they really changed the energy to they really put the equation of 1/2 mv squared equal to mct. Yeah, and after so. I'm pretty sure that we did more detailed presentation. Yeah.
How many minutes now?
Yeah, it's already over, but yeah, it's getting done soon.
Okay.
So
The temperature. So it's impossible to. Can you go back a little bit? Few slides. One more. So okay, this 39,000 Newton is impossible. Next. But then, how much can you raise the increased temperature? Can you calculate in the report? If you kick the ball many times, how much temperature can I increase? Please try to calculate in the report.
okay, so
And
okay.
If you can also try yourself.
Oh, okay, I'll do my best. Okay, so
Thank you.
Oh.
Very good.
oh, but in the end of this, in the end of our presentation, Eric is explaining the definition of a quantum superposition.
Okay, Eric.
Thank you.
Let's go.
Since we're running out of time, I will just chase the cut. So the new English, like the new physics term that we're gonna introduce is called quantum superposition, and this is a definition that you can read. And so I'm gonna, for your understanding, I will just explain you like in my way. So just think of a way that a coin is spinning in the air, and it's not just like heads or tail, but rather a blend of both until it lands, so we observe the result. So in terms of quantums, the act of measuring the system calls the wave function, which describes the superposition, to collapse into one specific state. And we're gonna show our Kahoot. So thank you everyone.
Thank you, Eric. So, Henry, please keep the time and make the sound much larger so that I can hear
Oh,
Otherwise, you cannot finish today in time.
oh,
Right?
okay.
No, I'm asking Kevin.
Oh.
Okay.
Wait, I cannot hear the bell of the 3 minutes, so make it louder, please. Or you speak up at 3 minutes. Can you do that?
Okay, I asked Darian to sit very close to the microphone so that you can hear the alarm.
Send a message at 3 minutes. Okay? Send a text message.
Okay, okay.
You do that? Thank you. Okay, everyone please join the couple. I only see Yo here.
Should I start? Oh, there's one more.
Yes, please. Okay. I don't remember the number. Numbers are so close.
Oh yeah, sorry.
Hey, so Darian, you remember the number?
Yeah, I remember the number.
Amazing. Okay.
So,
Thank you very much.
thank you.
Yeah, your presentations are all good. Yeah.
Yeah, thank you. Thank you for your time.
Okay. Shall we switch to the next group? Because we're running out of time.